Hello everyone and welcome to Mechlin 360. So in this video I want to solve a question to illustrate the Euler load, the crippling load. But you see that this question is about column. However, it has been associated with what? A beam. So basically you have to all the time compare. All right. We have here a simply supported beam of length 4 meters. Okay, so the length of the beam is 4,000 millimeters, and then it's subjected to a uniformly distributed load of 30 kilonewton per meter. So basically you have what we call the UDL of, or let's say the uniform distributed load of 30 kilonewton per meter. Okay, so 30 kilonewton per meter is the same as 30 kilonewton, so like 30,000 divided by per meter, so that's 1,000 millimeters. So basically we are going to get 30,000 newton divided by 1,000 millimeters. So in actual fact, we end up getting what? 30 newton per millimeters. Yeah. So that's basically the UDL over here. But it says that this over the whole span, and then deflects 15 millimeters at the center. Okay, so I've done a video about the deflection of beam when I have a simply supported beam, a UDL. So essentially, if you watch the video, you realize that if you have a simply supported beam, okay, and then it is having this form of UDL, the maximum deflection will actually occur at the center. And then the formula for the deflection will be given by 5 out of 384 WL to the power 4. And then this one will be divided by EI, essentially. Okay, so this is actually the formula for the deflection. But then the actual question is, we should determine the crippling load. That's, in other words, the Euler load when this beam is used as a column with the following condition. So one end fixed, other end hinge, and then both end pin jointed. So a pin is also the same as a hinge. Okay, but then basically if we use the Euler load, it's going to be pi squared EI divided by LE squared, where LE is the effective length, okay, depending on your end condition. However, this WL4 over 384 EI will give us the EI. Okay, so let's put everything together. Deflection is 15, 5 out of 384 multiplied by the load per unit length, which is 30, and the length itself, which is the span of 4,000 to the power 4, and then so divided by EI. So essentially it is the EI that we are after, because once we have EI, we can go ahead and then calculate the Euler load since we have the EI. So basically, if we make EI the subject, we are going to get what? 15. Okay, so make EI the subject is pretty much simple. Let me take my time and do this. So 15 multiplied by 384 multiplied by EI will be equal to 5 multiplied by 30 multiplied by 4,000 to the power 4. Essentially, if I make EI the subject, that's going to be 5. So 5 multiplied by 30 multiplied by 4,000 to the power 4, and then divide this by 15 multiplied by 384. If I do this, what EI? So EI is going to be 5 times 30 multiplied by 4,000 to the power 4, and then I will divide this by 15 multiplied by 384. So that's giving me such a huge figure for the EI, which is 6.67 times 10 to the power 12. So essentially, EI is called flexural rigidity, okay, or sometimes the stiffness of the beam. So Newton millimeter squared. So right now that I have EI, I can now go ahead and find the Euler load. So for the first condition, okay, so pi squared EI divided by LE squared. So pi squared 6.67 10 12 all divided by LE squared. The first condition says one end fixed and other end hinge. Now, as a matter of fact, if you have one end fixed and then the other end hinge, the the Euler load is going to be okay, so it's going to be 2. Okay, let me write this here. Yeah, so it's going to be so the effective length, if it is fixed at one end and hinge at one end, is going to be L divided by root 2. So essentially, let's do that. The length of this beam is 4,000, right? So what is this? It's going to be 4,000 divided by square root of 2, and that will give us the effective length. So that's going to be 4,000 divided by root of 2. And that's 2828.427. 2828.427 millimeters. And then that's what comes here. Squared. So essentially, if it is fixed at one end and hinge at the other end, the Euler load is given by pi squared multiplied by 6.67 times 10 to the power 12 divided by 2828.427 squared. So that's the Euler load for you. So essentially, okay, so that's essentially what you get. But it must be noted that depending on how you do it, your answer may change. So for this one, we are getting 8228.8 kilonewton. But if you decide to LE is L over root 2. So if you decide to say that you are going to do pi squared EI divided by L over root 2 squared, this one will become, because of the root 2, is going to be 2 pi squared EI divided by L squared. So this is also correct. So depending on how you do it, you may get some approximations. I want you to do this same question using this formula and then give me your answer in the comment section. Okay, use this formula when you substitute it rather. Now let's look at the other problem where it says both ends pin jointed. Okay, so a pin joint is like, again, like a hinge. So that one is straightforward. Pi squared EI over LE squared. But if it is pin jointed, then the LE is the same as the length. So this one, there is no two ways about it. Pi squared 6.67 times 10 to the power 12, all divided by 4,000 squared. And then that's going to be, so I'll just come here and then divide this by 4,000 squared. So essentially that's like 4114.4. 4114.4 kilonewton. So what this means is that, clearly speaking, if we do it hinge, what do you expect? We are getting 4114. But if we do it one end hinge and one end fixed, we are getting almost times 2 of what we have. All right. So that's this problem solved for you. Thank you very much for watching.